This is Group Harry, Neha, and Kevin, and we're working on the 1982 Physics C AP exam. Um, we're looking at the question that reads, a 20 kilogram mass released from rest slides 6 meters down a frictionless plane, inclined at an angle of 30 degrees with the horizontal, and strikes a spring of spring constant K equals 200 newtons meter, as shown in the diagram above. Assume that the spring is ideal, that the mass of the spring is negligible, and that the mechanical energy is conserved. So part A of this question asks us to determine the speed of the block just before it hits the spring. And to do that, we're going to look first at the block's energy, starting with its potential energy due to gravity at the top of the plane, and setting that equal to the kinetic energy it will have just before it reaches the spring. So if we break down these equations, we have mgh equals 1/2 mv squared. We can see right away that the masses cancel out, and we're left with gh equals 1/2 v squared. So we can break these down further with g, and then looking at the height, we want just the height that the block travels down as it goes to the spring, which would be the 6 meters distance it is already displaced from the edge of the spring, and we want only the vertical component of that. So we will take the 6 meters distance and multiply that by the sine of 30 degrees, which is the angle that the ramp is above horizontal, and that will be set to the 1/2 v squared. So with a little bit of rearranging, we reach v equals the square root of 12g sine of 30 degrees, and we plug in g equals negative 10 meters per second squared. For our velocity, we reach 7.75 meters per second, just as the block is reaching the end of the spring. So moving on from part A, now we're going to look at part B, which asks us to determine the distance the spring has been compressed when the block comes to rest. So once again, we're going to be looking at energy here, and we're going to set the potential energy due to gravity that the block has at the top of the plane equal to the spring potential energy. So we're going to break these down again. We'll have mgh equals 1/2 kx squared. So we can drop these down to mg. Now for our h, the height is once again only the vertical component, but now we have to compensate for the extra vertical distance that the block travels down when the spring compresses. So we have our 6 just like in part A, but we need to add the x distance that we'll use over here too, that the spring compresses. And then because we're only looking at the vertical component, we're going to multiply this by sine of 30 and set this equal to the 1/2 kx squared. So we can do some algebra, but I don't really feel like doing that, and we're just going to plug in the 20 kilograms here for the mass, multiply that by 10 for our gravity, 6 plus x, sine 30, and the rest of this, and then 200 Newton meters for our spring constant and x squared. And when it's all said and done, with just some rearranging and plug it into your calculator, x equals 3 meters. So the block will compress the spring 6 meters before it comes to rest. Okay, so we've done part A and part B, so now we're going to do part C. And part C asks the question, is the speed of the block a maximum at the instant the block strikes the spring? And asks us to justify our answer as well. So, to put it simply, no, the block isn't at a maximum velocity at the instant it strikes the spring, because the net force on the block is not zero. And if we look at the forces acting on our block, we have our Fg coming out of here, but we are looking at the x component. So we can, I'm going to come down here. We have our Fg, and then because we're only looking at the horizontal component, which is accelerating it down the ramp, we're going to multiply it by the cosine of 30 degrees. And in order for the block to start decelerating, the opposing force, which is our spring force, which is US, but we're going to write it as negative kx. This force needs to be greater than the force of gravity in the horizontal direction in order to make the block to start slowing down. And in order for it to do that, this x value needs to be greater, so the spring needs to compress a little bit. And it doesn't ask us to solve for the distance, but it actually works out really nicely. And we have our mg cosine of 30 degrees, and this is equal to a negative kx, and our mass is given to us, just 20 kilograms. We can multiply this by negative 10 meters per second squared, our gravity, and we have cosine of 30 degrees. And this equals our negative, and then the spring constant is 200, and then we're just left with x. So we can cancel out our negative 200s, and we have x equals cosine 30, which is conveniently given to us at the top of the page right here, and it tells us that x equals 0.866 meters.